For exam 2, you'll need to know Newton's 3 laws. And Newton's first law is the law of inertia, namely an object set in motion or at rest will continue in that state unless acted upon by an outside force. Newton's second law says that the net force, or the sum of the forces, is mass times acceleration, where the mass is the mass of the object that's experiencing the net force. And Newton's third law says that the force on object 1 due to object 2 is the same as the force on object 2 due to 1, but opposite in direction, hence the minus sign. So for example, the reason why you're able to walk from point A to point B is because your foot pushes the ground to the rear, and the floor responds, or ground responds, by pushing you to the front. Equal forces, opposite in direction. You'll need to know Newton's law of universal gravitation. And it says that if you have two masses separated by a distance r, the gravitational force of attraction is written like this. So for example, if this was the mass of the Earth, and this is the mass of your person, the equation would be the gravitational constant, 6.67 times 10 to the negative 11, times the mass of the Earth, times the mass of your person, divided by the distance. In this case, it would be the radius of the Earth. And here, what I circled, g times mass of the Earth divided by the radius of the Earth squared, and this is called the gravitational field, or 9.8 meters per second squared. That's the gravitational field acting downwards at the Earth's surface, or at around sea level. Now, feel free to interrupt me anytime. And here we have the gravitational redshift formula. Astronomers like to use a symbol Z when talking about redshift. And the physical interpretation here is that, as an example, the sun emits a photon of light of wavelength lambda 0. And on Earth, we detect that radiation, but instead of having a wavelength of lambda 0, it has a larger wavelength, and hence we say a redshift occurred. And if you take that displacement and divide by the original emission, we see that it's proportional to the difference in potentials. The potential at the sun's surface and the potential at the position of the Earth. Capital R is the radius of the sun. If you're talking about a wavelength of light that was emitted at the surface of the sun, and R would be the distance between the Earth and the sun if we're talking about the wavelength being detected on the Earth. Einstein doesn't include this term. He just throws it away because 1 over the distance of the sun-Earth distance is pretty much 0 compared to this value here. Okay. So just keep that in mind. This second lambda refers to this one, and this one refers to this one here. Okay. You could also talk about a blue shift. So for example, if light was emitted at the surface of the Earth and then arrived at the sun, the wavelength would actually decrease. The wavelength would decrease. Okay. Any questions so far? If you're talking about a blue shift, you have to interchange these two terms for a blue shift. Okay. For a blue shift, then the original wavelength would be, you put lambda over here, and lambda down here, and lambda 0 over here. And then lambda would just be interpreted as the wavelength emitted at the surface of the Earth. And then lambda 0 would be the wavelength detected at the surface of the sun. And if you and I could live on the surface of the sun, which is impossible, we would see the wavelength to be contracted. Okay. Now, I think in the quiz, I mentioned that in quiz 6, the blue shift and the red shift formulas. I think they're at a different frequency. Next is the gravitational time dilation. And we did 2 examples, one for GPS satellites and the other for the time discrepancy between, say, your head and feet on the surface of the Earth. And for a GPS satellite, we use the Latin letter T for the time that occurs for an orbiting satellite. And we use the Greek letter tau for the time, for the corresponding time on a ground-based clock. And that time difference between the satellite and the ground-based clock is proportional to that term we just talked about before. So notice again, you have the GM over C squared like before. And now when it comes to this difference, how do we read it here? So R, capital R here is the radius of the Earth. And that corresponds to tau, the time that occurs on the surface of the Earth. So it looks very similar to up here. R is the radius of the sun, and that corresponds to where the photon of light was emitted. And the Latin letter T corresponds to the time where the satellite is located out in space. And that position is a distance from the Earth's center, and that distance is the radius of the Earth plus the height above the ground. And so if you just want to find the time difference, you just have to use this formula and make sure you multiply by the time, the ground-based clock. You can write it a little bit differently. If you remember that the gravitational potential is this guy here, negative GM over R, you can write that time difference between the GPS satellite and the ground-based clock as a difference in potentials. And this is the potential at the surface of the Earth, and this is the potential at the position of the satellite, orbiting satellite. So I wrote the subscript R plus H and subscript R to designate those 2 unique positions. And if you want to find the time difference between your head and feet, you can still use this equation here. But one can show using something called a binomial expansion, which you're not required to know or remember, but I'm sure you probably did in high school. You can write this stuff this way here. And our interpretation here is that a little t is the amount of time by which the clock runs faster at your head than your feet. Again, lowercase t represents the amount of time at which a time runs faster at your head than your feet, and capital T represents the total time that elapses, say, at your head. And if you take the ratio, you get the GH over C squared. And so whenever you compute this ratio, G would be the 9.8 meters per second squared, assuming you're at the ground. H is your height, say 6 feet. C squared refers to the speed of light squared. That ratio is just simply the time difference between your head and feet divided by the time that elapses at your head. And if you multiply this by 100, you can cast it in percentage terms. the percent by which time runs slower at your feet than your head. So again, if you multiply this by 100, represents that the percent by which time runs slower at your feet than your head. Any questions so far? And lastly, you need to know conservation of mechanical energy, and namely potential and kinetic, the summation is conserved. And subscript I just means initial, subscript F just means final. So this is the initial total energy, this is the final total energy. And the potential energy is also known as positional energy, and kinetic energy is also known as motional energy. And potential is just mgh, and kinetic is the 1/2 mv squared, okay, for energies. And you want to be careful, this potential here and this potential here, they're almost the same thing. They're almost, the only difference is mass. So if I multiply this potential here by the mass of the orbiting satellite, then this becomes the gravitational potential energy. Okay. The reason why these two look different is because someone did something called a binomial expansion, and we wrote this as this. But you don't have to worry about that. You can just Google it if you're interested, or you can ask me about it later. Any questions about this? And then I wrote just some warnings. Make sure you have an algorithm for doing the problems. If you're comfortable with quiz 6 and the notes, you should be fine. Now, if I were you, I would just maybe redo the calculation just to make sure you're comfortable using your calculator, using the powers of 10 and the parentheses, for example. Don't take for granted that just because you read it, that you know it, right? And that applies to me too. I notice sometimes if I just read something, I think I know, but then it's not till I apply it, do I really know if I know. And so these are problems I find students often encounter. Maybe they're using a calculator with which they're not comfortable. So hopefully you'll use the same calculator that you've been using. And another problem sometimes I notice is not being patient. You have plenty of time, so there's no rush. All right. And that's all I have to say about the exam 2. Any questions about it? And it's actually available right now. And here's the exam 2. And you have 2 hours to take the exam until Sunday night. And if you can't take it, you need to contact me ASAP. All right, don't wait till the last second. And maybe you didn't notice this, but you get 2 cracks at it. All right, you get 2 cracks at it. With that said, there's nothing surprising. Like I said, if you know quiz 6 and you follow the calculations, the notes, I think it should be straightforward. And well, also, if you walk away from the exam, the clock keeps ticking. And this is one thing you should definitely be aware of. If you score higher on your first try than your second try, Unfortunately, your last try will be the only one recorded. So it's only the last try that's recorded. So don't be unmindful, if you will. Okay, try to be careful. So if you plan on taking it again, make sure you record your choices before you move on. Okay. Any questions so far? And what about quiz 6? Everyone happy? Everyone's happy with quiz 6? All right. Let's go on to Einstein's text. I want to point out that there might be a problem if you're using a different text than the one we're using in class. And for whatever reason, a couple of you had emailed me about using a text online, and I think I sent you this one here. You can see the website bartleby.com. You access this via, so I found this via Wikipedia. Wikipedia has an article on Einstein's text, and down below they have this link here. But this edition that they posted in Bartleby is it's older than our edition, and you can see it here. So if you look at section 29, where Einstein talks about the consequences of his general theory of relativity, he mentions that, let's see here, I do not doubt that these deductions will be confirmed, but if you look at our assigned text, he says the opposite. He says that they have been confirmed, and which means that this edition was written when the shift in the spectral lines, for example, of the light coming from, say, Sirius B, wasn't detected yet. Okay, wasn't detected yet. So just keep that in mind if you're using maybe an older edition. All right, let's go to section 27. And if it's okay, I'm going to call on you and ask you to read. And if you're not comfortable reading, just let me know. And it's not a big deal. I'll just ask someone else. I don't want to read everything to you. I thought we could read it and then try to see, or I will try to explain to you what it's talking about, what Einstein is telling us. And of course, you're welcome to ask questions, make comments. So here again is section 27. This is space-time continuum of the general theory of relativity is not a Euclidean continuum. And we talked about that last time, right? That space-time is curved given the presence of gravity. Is Anna Creaser with us?
Yep, hello.
Hi, Anna. Would you mind reading this first paragraph for us?
Sure. In the first part of this book, we were able to make use of space-time coordinates, which allowed of a simple and direct physical interpretation, and which, according to section, I'll be honest, I don't know that one.
26.
26 can be regarded as four-dimensional Cartesian coordinates. This was possible on the basis of the law of the constancy of the velocity of light, but according to section, which one is that?
21.
21, the general theory of relativity cannot retain this law. On the contrary, we arrived at the result that according to this latter theory, the velocity of light must always depend on the coordinates when a gravitational field is present. In connection with a specific illustration in section, is that 23?
Yes, ma'am.
We found that the presence of a gravitational field invalidates the definition of the coordinates and the time, which led us to our objective in the special theory of relativity.
Thank you very much, Anna. I want to draw your attention to some parts of this. Let's see, he mentions that phrase, law of the constancy of the velocity of light. You recall that in the special theory of relativity, we have two postulates. One postulate is that the laws of physics are the same when switching between inertial frames. And the other postulate is that the speed of light is constant. Furthermore, in the special theory of relativity, the velocity of light is also constant. That is, it moves in straight lines apart from entering, say, a new medium, for example, when we talked about refraction. So we're just talking about vacuum here. And so again, in special theory of relativity, you can think about Euclidean space or having a Cartesian coordinate system where you can draw lines indefinitely straight. But we saw there in section 21, with the general principle of relativity or the equivalence principle, that the velocity of light is not constant. It's not constant. Remember, there's the starlight deflection. Whenever light comes close to our sun, it gets deflected. That's also talked about in appendix, I think, 3B. And so that's something that Eddington and others went and confirmed in 1919 after the conclusion of World War I. But if light is going to be deflected by the presence of a massive object like our sun, then that means that we can no longer talk about straight lines. No longer talk about straight lines. That is, space-time is curved. Now, this means that we have to dispense with our notion of Euclidean space and also a Cartesian coordinate system. And then he goes on and mentions section 23. Section 23, you may remember, refers to that spinning disk. And by the equivalence principle, we said that instead of thinking of a spinning disk, you can instead think about a gravitational field that emanates outwardly from the center of the disk. So remember, again, the equivalence principle says that the physics in an accelerated frame is going to be the same physics if you dispense with the accelerated frame and instead go with the presence of a gravitational field. And we saw with the spinning disk that things become kind of weird, right? For example, if you have an array of clocks situated along the radial arm of the spinning disk, and if you were to walk or observe the clocks from the center to the periphery, you would notice the clocks run at different rates. The clocks run at different rates. So before the gravitational field was turned on, all the clocks ran at the same rate. But once the gravitational field was turned on, and we said that it's stronger at the periphery of the disk, the clocks run slower where gravity is stronger, and the clocks run faster where gravity is weaker. All right. And then also we mentioned the circumference is no longer 2 pi r. It's no longer 2 pi r. In Euclidean space, or having Cartesian coordinates or a Cartesian grid placed upon Euclidean space, you can talk about drawing straight indefinite lines onto infinity. You can talk about having circumference being 2 pi r, but with this presence of the gravitational field, that is thinking about the deflection of starlight, or this or in the case of the spinning disk, that is thinking about a gravitational field emanating outwardly from the center, we no longer have this Euclidean space. We can no longer superimpose a Cartesian coordinate system made up of squares throughout. Instead, if you were to, for example, have a rod on your person and walk from the center of your disk outwardly to the periphery, because of the presence of gravity, that rod will be distorted. That rod will be distorted, right? Just like the wavelength of light, when it leaves the sun and gets to us, it gets stretched. And for this reason, we have to dispense with this notion of having rigid rods. And furthermore, we can't have clocks all set to the same time. And so simultaneity becomes a problem, right? Simultaneity becomes a problem. Any questions about that? And he says in the next paragraph, in view of the results of these considerations, we are led to the conviction that according to the general principle of relativity, the space-time continuum cannot be regarded as a Euclidean one. Okay? In other words, there's curvature, hence explaining the warping of time and space. Let's see, I want to read something else here. Anthony, are you with us? Anthony Marguerite. Bridget Anthony, are you with us?
I'm here.
Would you mind reading the text in blue for me, please?
Sure. Just as it was there impossible to construct a Cartesian coordinate system from equal rods, so here it is impossible to build up a system, reference body, from rigid bodies and clocks, which shall be of such a nature that measuring rods and clocks arranged rigidly with respect to one another shall indicate position and time directly. Such was the essence of the difficulty with which we were confronted in section 23. But the considerations of section 25 and 26 show us the way to surmount this difficulty. We refer the four-dimensional space-time continuum in an arbitrary manner to Gauss coordinates. We assign to every point of the continuum or event four numbers, x1, x2, x3, and x4 coordinates, which have not the least direct physical significance.
Very good, thank you. So we'll come back to this point of x1, x2, x3, x4 not having physical significance because he draws attention to where there is physical meaning. But first, coming back to the previous paragraph, he says it was there impossible to construct a Cartesian coordinate system from equal rods. So this takes us back to that marble slab. So remember, he said you heat up a marble slab and it causes a distortion in the overlaid Cartesian coordinate system made up of rigid rods. And so this goes along with our thinking, or it's a nice analogy to think about when thinking about, if you want to maybe explain to a person about how to think about space-time curvature. Just have a marble slab, have a Cartesian coordinate system laid with rigid rods, you heat it up. Well, now you see that the Cartesian coordinate system is no longer Cartesian. You can't draw straight lines, you can't apply Pythagoras' theorem, you can't say circumference is 2 pi r, okay? And he says, so the import of that message is we need to dispense with this notion of having rigid rods. when gravity is present. Okay. And then in this second paragraph, he gives us our recourse. He says instead, let's just use 4 arbitrary numbers or coordinates, x1, x2, x3, x4. He calls them Gauss coordinates. Gauss coordinates. Now these Gauss coordinates become the typical flat space time coordinates, that is 3-dimensional space and 1 time, when gravity is not present, when there is no space-time curvature. But in general, when you do have gravity present, one speaks about having these 4 coordinates to specify the space-time event, and they're again called Gauss coordinates or Gaussian coordinates. And he makes a curious remark that these 4 numbers have not the least direct physical significance, all right? All right. And then I want to, so then let's try to impose meaning. Let's see here. Let's see. Chris Hart, are you with us?
Yeah, I'm here.
Would you mind reading the text in blue, please?
Yeah, of course. In the same way, any such lines in our continuum correspond to many points in motion. The only statements having regard to these points which can claim a physical existence are in reality the statements about their encounters. In our mathematical treatment, such an encounter is expressed in the fact that 2 lines which represent the motions of the points in question have a particular system of coordinate values x1, x2, x3, x4 in common. After mature consideration, the reader will doubtless admit that in reality, such encounters constitute the only actual evidence of a time-space nature with which we meet in physical statements.
Very good, thank you. So a question for anyone, what does he mean after mature consideration? The reader will doubtless admit that in reality, such encounters constitute the only actual evidence of a time-space nature. Why does that make sense? That's only with encounters that we can talk about physical meaning, namely time-space. Whereas if you're not talking about encounters, when it comes to those coordinates, don't assign meaning to them, just say they're general coordinates. You can just tell me, or you can put in a chat box, either way. Just in case you're not clear, when he talks about lines here, what he's talking about is the trajectory of, for example, a moving particle. You can imagine a particle moving, and if you were to take a crayon and follow the motion of the particle, you can imagine that you form these curved trajectories, right? And what he's saying is that an encounter refers to an intersection of these 2 different lines. That is, these 2 different particles are moving, so they meet at some point. And it's only when they meet that you can talk about a physical meaning associated with those 4 coordinates, in this case, where they meet at. And the physical meaning therein would be it's of a time-space nature. So let me ask you both a question. Okay, so let's see, someone left me a chat. Right, okay. So someone said it's because that such encounters give you something to base the coordinates off of and make them real. All right, so that's correct. But I want you to be a bit more explicit. And so suppose I asked you folks, or I told you folks, we're going to have a meeting. And that's all I told you, we're going to have a meeting. What would be your immediate question or questions to me?
What's the time and place?
Beautiful. What's the time and place? Very good. Very good. Right. So likewise here, and so Einstein, he sounds kind of philosophical here, right? By using that word encounter and saying that's only when you have encounters do you have meaning in a time-space nature. It makes sense because if you tell me you want to have a meeting, my question to you is, well, where and when? That is, give me the time and space so we can meet, right? Very good. Now, any questions so far? Let's go to the last paragraph. Is Gabby Larissa with us?
Yeah, hi, how are you?
Doing well, thank you. Would you mind reading this paragraph in blue, please?
Sure. Every physical description resolves itself into a number of statements, each of which refers to the space-time coincidence of two events, A and B. In terms of Gaussian coordinates, every such statement is expressed by the agreement of their four coordinates x1, x2, x3, x4. Thus, in reality, the description of the time-space continuum by means of Gauss coordinates completely replaces the description with the aid of a body of reference, without suffering from the defects of the latter mode of description. It is not tied down to the Euclidean character of the continuum, which has to be represented.
Very good, very good. So every physical description involves an encounter. Every physical description involves an encounter. Okay. We're going to use Gaussian coordinates. That is, we're dispensing with Euclidean space and using a Cartesian coordinate system. Why again are we dispensing? Because we said that the presence of gravity involves the fact that we can no longer use this notion of having rigid rods laid down to make our Cartesian coordinate system. We can no longer have neighboring clocks with the same time when they're arrayed along the direction of the changing gravitational field. So if we can't have such things, if we can't have such a Cartesian coordinate system, we can't have rigid rods to make it, then naturally we have to throw out the body of reference also, which would hold it. So if we're throwing out the Cartesian coordinate system along with the body that would hold it, what we're saying is that the presence of gravity requires a coordinate-free description. The presence of gravity requires a coordinate-free description. Hence, the use of these arbitrary four coordinates are Gauss coordinates, which have no physical significance. Okay. So again, we threw out our Cartesian coordinate systems along with the body of reference that would hold it. And what are we left with? We're left with a coordinate-free description, our Gauss coordinates that have no physical significance. Let me show you something on Wikipedia. We had mentioned the Schwarzschild metric last time, and there it is right here. And if you look down below, if you just go to Google and type in Schwarzschild metric, you'll come to this Wikipedia article here. And if you scroll down, you'll see that you can write alternative metrics using different coordinates. All right, so you can go with the Schwarzschild metric, or you can go with the Eddington-Finkelstein coordinates. You can go with these other coordinates, and so each of these sets of coordinates, they have their usefulness. Okay, they have their usefulness. As an example, when Schwarzschild first wrote his metric here, we mentioned that there's a singularity at r equals 0, right? You can't have 1 divided by 0, where r equals 0 would be the center of the black hole. And another singularity problem would be when r is equal to the Schwarzschild radius. The Schwarzschild radius is the event horizon, or the radius of the black hole. So once you go into the surface, you're not coming back out. Even light that goes in can't come out. And you can see in this equation when the position is right at the Schwarzschild radius, you get 1 here, and 1 minus 1 is 0. Here it looks fine, but notice here is raised to the -1, which means that when the position is at the Schwarzschild radius, you have 1 over 0. So originally, when Schwarzschild first wrote this down, people thought that, okay, this is also a singularity. You have two singularities, r equals 0, and also at the surface. But then it was found later that the only true singularity is at r equals 0. There is no singularity at the event horizon. There is no singularity at r equals the Schwarzschild radius. And to see that properly, you have to switch to a different coordinate system, or different Gauss coordinates, to see that properly. Okay. So that's one example of wanting to switch coordinates so as to get away from particular problems. Okay. Yeah, so for example, here, if r is equal to rs, this is 0, but that's fine. Everything else is fine, so there's no problem. So people say you should use the Eddington-Finkelstein coordinates to get rid of that false singularity. You're not required to remember that for the exam. I just wanted to point out to you this idea about Gauss coordinates. You can go from coordinate system to coordinate system. All right, that's all I wanted to say about section 27. Any questions, comments? Now let's go on to section 28. And in section 28, we're looking at the exact formulation of the general principle of relativity. So you might recall at the beginning of part 2 of the text, Einstein set that goal for generalizing the principle of relativity. And here he brings that goal to a conclusion. Is Hunter Bradbury with us?
Yes, I'm here.
Would you mind reading the text in blue, please?
Yep. We are now in a position to replace the provisional formulation of the general principle of relativity given in section 18 by an exact formulation. The form there used, all bodies of reference, K, K1, etc., are equivalent to the description of natural phenomenon, formulation of the general laws of nature. Whatever may be their state of motion cannot be maintained because the use of rigid reference bodies and the sense of the method followed in the special theory of relativity is in general not possible in space-time descriptions. the Gauss coordinate system has to take the place of the body of reference. The following statement corresponds to the fundamental idea of the general principle of relativity. All Gaussian coordinate systems are essentially equivalent for the formulation of the general laws of nature.
Very good, very good. I think he says it pretty well there. It sounds pretty abstract, I think, in the the final statement, but it's okay. In the next paragraph, he gives us another way of articulating the matter. So just keep in mind. So again, in section 18 or section 19, he sets the goal that or he reminds us that one of the postulates of special relativity is that the laws of physics should be the same when switching between inertial frames, and he sets out the goal that he wants to generalize that law. He wants the laws of physics to be the same regardless of your reference frame, regardless of whether you're in an inertial frame or whether you're in non-inertial frame. For example, gravity is present. But then he goes on and says that we can't use rigid rods to make up a Cartesian coordinate system. We have to throw out such thinking, and hence we have to also throw out the Euclidean space that would hold it, or the reference body that would hold it. And we're left with now a coordinate-free description. And the end of that journey then is this final statement here, that the general principle of relativity is to be said to be such that the general laws of physics hold when going from one set of Gaussian coordinates to another. The general laws of physics, they hold when going from one set of Gaussian coordinates to another. Let's see. I want us to look at this paragraph here. So in this paragraph here, he says that he's trying to make things more intelligible for us. So let's see if it's any better. Karen Mortimer, are you with us?
Yeah, I'm here.
Would you mind reading this paragraph for us, please, in blue?
Sure. According to the special theory of relativity, the equations which express the general laws of nature pass over into equations of the same form when, by making use of the Lorentz transformation, we replace the space-time variables x, y, z, t of a Galilean reference body k by the space-time variables x prime, y prime, z prime, t prime of a new reference body k prime. Reference body k prime. According to the general theory of relativity, on the other hand, by application of arbitrary substitutions of the Gauss variables x1, x2, x3, x4, the equations must pass over into equations of the same form. For every transformation, not only the Lorentz transformation, corresponds to the transition of one Gauss coordinate system into another.
And you accelerated there. It's okay. It's okay. Good job. According to the general theory of relativity, on the other hand, by application of arbitrary substitutions of the Gauss variables, the equation must pass over into equations of the same form. Okay, very good. All right. Let's see here. Just in case you may have forgotten, and also, so he makes references to previous material in the text. And just in case you forgot, when he says Galilean law, what he means is Newton's first law, or law of inertia. Okay, so just keep that in mind. So this would be when there's, or when we're using an inertial reference frame. Okay. So again, Galilean law refers to Newton's first law, or law of inertia. And he talks about Galilean domains. He's talking about inertial frames where you have Newton's first law holding. Okay. So I think that's all I wanted to mention there in section 28. Okay. Let's see. Look at one other thing here. Let's see. Jackson, are you with us?
Yes, I'm here.
Thank you. Would you mind reading the text in blue, please?
Yes. In gravitational fields, there are no such things as rigid bodies with Euclidean properties. Thus, the fictitious rigid body of reference is of no avail in the general theory of relativity. The motion of clocks is also influenced by gravitational fields, and in such a way that a physical definition of time, which is made directly with the aid of clocks, has by no means the same degree of plausibility as in special theory of relativity. For this reason, non-rigid reference bodies are used which are as a whole not only moving in any way whatsoever, but which also suffer alterations in form ad lib during their motion. Clocks for which the law of motion is any kind, however, irregular, serve for the definition of time. We have to imagine each of these clocks fixed at a point on the non-rigid reference body. These clocks satisfy only the one condition, that the readings which are observed simultaneously on adjacent clocks differ from each other by an indefinitely small amount. This non-rigid reference body, which might appropriately be termed a reference mollusk, is in the main equivalent to a Gaussian four-dimensional coordinate system chosen arbitrarily.
Thank you very much. Here Einstein is just saying, look, we have to still talk about space and time. So we just do the best we can and just accept the fact that in this non-rigid reference body, when you have clocks next to each other, they're going to be different. And hopefully they're still close enough that one can still carry out a meaningful investigations. Okay. All right, let's go on to section 29. And that's the last section of part 2. And next week we'll do 30 to 32, and that's cosmology. I think intellectually, I think 24 to 29 is probably the most challenging, to take some time to kind of just accept this coordinate-free description. I like how he begins here in section 29. He says, if the reader has followed all our previous considerations, he will have no further difficulty in understanding the methods leading to the solution of the problem of gravitation. In the second half of this section 29, let's see here. Let's see. He goes on to consequences of his general theory of relativity. Kelly Johnson, are you with us?
Yeah,
Would you mind reading the text in blue, please?
okay. The theory of gravitation derived in this way from the general postulate of relativity excels not only in its beauty, nor in removing the defect attaching to classical mechanics, which was brought to light in section 21, nor in interpreting the empirical law of the equality of inertial and gravitational mass, but it has also already explained a result of observation in astronomy against which classical mechanics is powerless.
Oh, very good, thank you. I hear this last part when he says his general theory of relativity has explained something in astronomy which classical mechanics is powerless. He's here talking about the precession of the perihelion of Mercury. We saw that video last time of Tyson talking about, I also posted a video under announcements in Sakai if you haven't seen it. In that video, Tyson talks about the orbit of Mercury about the sun. And classical mechanics, or Newton's law of universal gravitation, explains two things about Mercury going around the sun. One, the reason for the elliptical orbit around the sun is due to, you can derive it from Newton's law of universal gravitation. And the second thing is that the elliptical orbit itself, the whole orbit actually rotates. And the reason why it rotates is because the outer planets, Venus, Earth, Mars, and Jupiter, are tugging on the orbit of Mercury. And in that video, Tyson said that there was an extra amount of rotation that was not explained by Newton's law of universal gravitation, that is classical mechanics. And that explanation comes from the general theory of relativity. So that again is what Einstein's referring to here when he says, explain the result of observation in astronomy. So historically, when people saw that extra rotation, the thinking was that maybe there's a planet that we haven't seen that's super close to the sun. Maybe a planet called a Vulcan, right? Or maybe there's something else there, right? Something physical, but no, it's actually the curvature of a space-time. And so as Mercury gets very close to the sun, that is approaches its closest point called the perihelion, is traveling through more space because the space is curved. And because it's traveling through more space, when it comes back out of that funnel, if you will, its orbit has been rotated. Okay. And at the end of this section, so you can tell this is an old edition because he says, I do not doubt that these deductions from the theory will be confirmed also. I don't know if you're looking along with your actual text that was assigned for the course, but you'll see that in our text, it actually reads, these two deductions from the theory have both been confirmed. And those two consequences that he's talking about are the curvature of light rays by the gravitational field of the sun, that is starlight deflection, and the displacement of spectral lines. For example, in the appendix 3C, I think in 1924, someone observed the shift of the spectral lines coming from Sirius B, which is a companion of the brightest star in the nighttime sky, Sirius. Okay. So at this time in history, when Einstein, or when this edition came out, you have these three correct consequences of the general theory of relativity. But today we have many, many more. So Einstein passed away decades ago, but today we also have the existence of black holes. In Einstein's day, the thinking was that, also by him, was that black holes are probably just mathematical aberrations of the general theory of relativity. They're not real. But today we actually have a picture of a black hole, and unsurprisingly, it's actually black. And also gravitational waves have been observed, which his theory predicted. And other things also, if you watch the videos I posted under announcements, you'll see what I'm talking about. And that's all I wanted to say about section 29. Any questions, comments about the reading? And so it's really a tiny amount of rotation. It's only 43 seconds of arc per century that the orbit of Mercury rotates. 43 seconds of arc per century. So remember that a circle has 360 degrees. A circle has 360 degrees, and each degree has 3,600 seconds. All right, so this is a pretty tiny fraction of a degree. It's so if you want to cast this in terms of degrees, you would take 43 and divide by 3,600, and that would be the amount of degrees by which the orbital trajectory of Mercury rotates about the sun per century due to just general relativity. All right, that's all I wanted to say. Next time we'll pick up section 30 to 32. We get into cosmology, which I think is interesting because Einstein, he ruminates or speculates about the cosmos. Is it finite? Is it spherical? And the nice thing is that this was written decades ago, and so he didn't know the things that you and I know today. They didn't have as powerful of a telescope as you and I have. They didn't have Hubble Space Telescope, for example, or telescopes that could see into the different wavelengths of light: X-ray, infrared, radio waves, for example. And today we have a much better picture than those folks decades ago in regards to our universe. Is it finite? Does it have a curvature to it? But still, it's interesting to see Einstein's take on it, and furthermore, how he goes about trying to speculate, how he uses reason and analogies to make his point. And we'll see where he was right, and we'll see where he was wrong. But I think the pleasure is in seeing his reasoning. I'll go ahead and let you go early, and if you have any questions, just let me know. But you're welcome to start the exam. You have until Sunday night, and I'll see you on Tuesday.
Thank you.
Thank you.
Thank you.
Thank you.